welcome to the MAVLink on modern network topologies talk. It's a lot more used, well-known network technologies. But I guess it's modern for the drone world, so yeah, let's get started. So yeah, this is Computer Science 101, OSI model network architecture. So we have the different layers, physical layers, network transport, all the way up to the application layers. Yeah, and the cool stuff about this is that the different layers don't have to know much about each other, right? So, for example, we have the TCP protocol, and that can runs on IP, but it doesn't itself have to know about IP. And then, actually, it works the best with HTTP, SSH, FTP, etc. These are all protocols that require guaranteed transmission. They require in-order transmission, and they all don't implement it themselves, so that's all implemented in the TCP layer, and they can all just forget about it because it's already done by a lower level. Yeah, I'm sure you know about this, so where does MAVLink fit in this? Is it like layer 7, 6, 5, 4, 3? So who thinks MAVLink is layer 5, 6, or 7? Raise your hand. All right. Who thinks MAVLink is layer 4? Layer 3? Right, yeah, you're all right. I mean, MAVLink does everything. Yeah, I mean, you know, MAVLink has a target system ID, target component ID. It has MAVLink router. It has all this stuff. So that's really like a routing protocol. That's really a network layer. It has MAV FTP. It has mission uploads, and they all have retransmission semantics. They have sequence number semantics. That's all TCP domain. And the best thing is they don't even share it. So MAVLink FTP has its own implementation of sequence numbers, and then the mission upload again has its own implementation of sequence numbers. So it's all a bit crazy. And yeah, I made a meme for that. It's like, so it's pretty much how we ended up here. But yeah, today I want to talk about this layer, layer 3. So what does MAVLink do in the routing domain? And how we can maybe make it a bit less crazy and use it and scale it, especially. So why talking about routing today? Mostly because of scalability issues. So we've seen in the past with some of our products and our applications that we've hit some scalability issues. And yeah, there's actually quite a few simple fixes that you can do to make it scale a lot better, which I want to talk about today. Cool. Yeah, routing scalability in MAVLink. That's really what the talk mostly will be about today. Yeah, what is routing? So again, Computer Science 101. You have a network, bunch of routers. Node A wants to send a packet to node E. So all the routers have to know how the packet will reach node E, and they forward it to the interface that goes into the right direction. This is an easy case where it's a directed acyclic graph. It's an acyclic graph, so there's no loops and crazy things. Yeah, so in IP, it works this way. IP has the concept of subnets, and each router has a routing table, and each and every packet, so very important, each and every packet has a destination, and every router compares the destination IP address of the packet that comes in against its routing table, and if a subnet of the routing table matches, it has an entry that tells it to which interface to forward the packet to. And yeah, this way your packet finds its way from top left to bottom right. This routing table also is either handcrafted, so in like the internet, a lot of ISPs and bigger autonomous systems, they handcraft these routing tables actually, because there's also a commercial interest there, so I mean you pay for traffic, etc. Or there's protocols like RIP or BGP that discover these links and set those up. Yeah, and it's actually quite cool, right? Because the routing table is actually significantly smaller than the space of possible IPv4 addresses. So you have about 4 billion possible IPv4 addresses. It's a 32-bit number. But each and every router only has to store a bunch of subnets. So, for example, your home router has just send everything to the ISP. And then your ISP has like this subnet goes here and this subnet goes here. So it's quite a few routes you only need to route the entirety of the internet traffic. And that's because of this subnet scheme. Now, yeah, MAVLink routing. So you may ask yourself, is there even such a case as MAVLink routing? I mean, MAVLink is just a drone protocol, right? Doesn't do routing. It's not quite true. So this is an actual system that we've encountered. And it has a lot of components, right? So you have PX4 running on an FMU, which would be the box on the left in the middle there. And if you've ever looked into the MAVLink module in PX4, you've probably discovered there's some code for a feature called MAVLink forwarding. And that code basically makes sure that when you receive packets on one UART interface on your FMU, that it routes them onto other UART interfaces on the FMU. And there's a whole bunch of logic in there to figure out to which UART interfaces it should actually route it to. So it is very much just like routing. It's like IP routing. Then you probably also have a companion computer these days, and on there you typically have a system called MAVLink, like a package called MAVLink router, or maybe you've implemented your own routing component there that takes MAVLink in and sort of distributes it to the right places. And you may have something like a camera handler and a gimbal handler and some off-board control thing. And then also your GCS. And then in your GCS, for example, if you buy a HereLink, it has, from stock, it has a MAVLink router installed. So with the feature to add multiple ground control software or even external devices that can again hook into MAVLink. And you suddenly are in a system where you have a lot of components, right? So here's 9 components. And yeah, you need to do some routing here. So yeah, how does it work in MAVLink? So we have a system ID and a component ID. Both are 8-bit. So in total, you technically have a 16-bit address space. So we have 65,000 total addresses that you could use. You're never going to get there because you'll have scalability issues way before that. Like even in below 100, you'll have scalability issues that will probably prevent you to get further. But yeah, technically, this is the total number of addresses. Now, a bit weird in MAVLink is that the source identifier, so the system ID and the component ID that denote the origin of a packet, so where a packet came from, it's actually part of the MAVLink header. So if you just can parse the header, you know where the packet came from. Interestingly enough, the target where the packet should go to is actually part of the message payload. So you can only ever figure out where a packet has to go to when you can actually decode the message payload. So if you don't know the message, you will have no chance of figuring out where the packet should go to, which is a very strange limitations in the system. And actually, almost more importantly, most messages don't even have these fields in it. So especially the telemetry messages, your battery message, global position message, and all those messages, they don't actually have a target. So you just send them out. Right, so here's an example of param request read. So that's the message you send to the Autopilot to request a param. And that has actually target information in there. So if your router understands this message, which it probably does because it has been there since 10 years, it can direct it. But then another message like this one is the good old heartbeat message, which is a classic telemetry message like battery status and so on. It doesn't have a target, so I mean, your router won't know what to do with this. So yeah, what does your router actually do, right? So I asked a whole lot of people to explain to me how MAVLink routing actually works. Like, how does it really work? How does a router decide where to put a packet to? If you go to the documentation on mavlink.io, you won't find anything described to this, and it's just not defined. It has been implemented a couple of times, but it was never defined. And if you look at the actual implementations there, which is like MAVLink router or how PX4 does it, you actually end up with this algorithm, right? So you come up with a new packet. So your router gets a new packet. And then you basically go to the left-hand branch here and you say, do I know this message type? Am I able to decode this message type? If not, what I'm going to do, even if this message had a target, even if this message was a directed message, I wouldn't know where it should go to. So I'm just going to broadcast it to all interfaces. You all have it. If I can decode the message, but it's a broadcast message, it's like heartbeat or it's battery status or something, nothing you can do, just broadcast it. Also that goes into the broadcast hole. And the last one do I actually know? You have a target, but do I actually know where that is? So did I actually ever receive a message from this system where this is supposed to go to? Then you can directly send it there. Otherwise, broadcast it. It goes everywhere. So you see, there's a lot of broadcast happening, and actually the majority of MAVLink traffic in an actual real system is broadcast traffic because of you need to be very lucky that it's not broadcast traffic, right? And then on the other end is actually when you receive a message from a system where you haven't received message from before, you have to put that into a routing table entry. So you have to maintain a routing table entry, and when you receive a message, you say, oh, okay, I know this system is there because I received a message from there. So technically, you have to have a database of all the messages, of all the systems you've seen before. Right, so in general, this looks like this, right? So top left wants to send a message to bottom right, and in case there's a telemetry message like heartbeat or battery status or global position or something like that, everybody gets it. You could say that's a feature. You could say it's a lot of unnecessary traffic. You know, it is what it is. Also, if you write a custom message, so if you have two components on board that need to send each other a custom message and the router doesn't understand it, it will send it everywhere, including the GCS and the FMU and the parachute and everything. And the other disadvantage is actually because there's no subnets, every router has to create an exhaustive list of every system that's there. So in the extreme case, if you would use every address in the system, every router would have to have a routing table that's 65,000 entries long to actually know for every one of those systems where to reach it, because there's no concept of subnets or something that we have in IP networking. So how big is the routing table in PX4? It used to be 16. It wasn't enough, so recently we've increased it to 32, so now you can have 32 systems. But it's clearly not, this clearly won't scale, so yeah. Right, so what is actually, it's routing, not touting, so that was a typo. But so the majority of MAVLink traffic is actually broadcast. So there's a lot, the more systems you add to a MAVLink network, the more traffic you generate for everybody in the network, not just for direct communication that is in there. There's also no assignment for these system IDs, component IDs, so far that's just always been hard-coded. There has been people talking about MAVDHCP, but I guess we know the meme, right? And also, things that we probably really want, like authentication, encryption, is just really hampered by this. So first of all, if routing information is part of the payload, you can't just have the routing information plain text and then the payload be encrypted, because otherwise nobody on the way would be able to read it, and then, it's broadcast again. And this whole broadcast nature of it also actually makes it quite hard to do end-to-end encryption, because everybody will need the keys to decrypt it, and then key management becomes really hard. On the website it says MAVLink is very well suited for application with very limited communication bandwidth, and MAVLink is highly optimized for resource-constrained systems. That may be true, but as soon as you add routing, it's definitely not true, because then you start adding actually a lot of unnecessary traffic. Let's say you add a system that only cares about one specific message, but it will still have to parse the entirety of the broadcast traffic on the entire network just to find this one specific needle of a message of all the traffic that it gets. And therefore, this is really where the scaling stops. So how do we fix it? Right, so as said, as long as you have one-to-one communication and don't try to do any fancy routing and stuff, it's actually fine. It's actually a pretty good protocol, right? The message set is highly optimized for drone use cases. It has been adopted in industry. People know how to use it. It's very easy. And, we should preserve that. But maybe this whole routing thing, maybe it just doesn't work. Maybe we should just get rid of that. So we have a protocol that solves routing. It's called IP. We have a protocol that solves drone messaging. That's MAVLink. Let's try to keep the compatibility, because that's the whole point of what we're trying to do, right? So that existing systems remain compatible and all. So let's keep the encoding. Let's keep everything there. But switch to IP routing and prefer to do one-to-one communication here. So how does that look in practice? So if in most modern systems, most of the communication runs over IP networks anyway. So if you have a more modern drone which has an IP radio connected to it, I mean, every packet that you send already has a UDP, an IP and a UDP header attached to it. So the packet on the wire really looks like this. You have an IP header, you have a UDP header, and then you get a MAVLink header, and then you get a MAVLink payload, right? I mean, let's just use the IP header that we already have. So IP header, you get source IP and destination IP. Amazing. And then you get the MAVLink header with the source system ID and component ID. And what I'm proposing here basically is, let's just ignore these system IDs. And it might sound like a fairly strange proposal, but hear me out. Right. So if we deprecate the system ID field in MAVLink, and we just say a system is an IP port combination that we can send data to and where we can receive data from. So your drone has an IP address, there's a port on that IP address, which is the MAVLink endpoint, and you can send MAVLink data there, and they can send MAVLink data to you from that point. At that point, if you can reach that IP address and that port, there's no need to have a system ID. You can just, if you receive data from that IP and port combination, you know it's coming from that drone. And if you want to send data to that drone, well, just send it to that IP and port combination. There's no need to think about this system ID at all in that case. If you want confidentiality, if you want authentication, use something like DTLS, standard UDP-based TLS, TLS implementation. It works with certificates and just the standard stuff. And you get industry cutting edge, well, maybe not cutting edge, but like industry standard encryption. And yeah, that won't work. And just don't forward the MAVLink stream left and right to everybody around you, which is probably not great for security and confidentiality. So in practice, if you have a multi-drone network, let's say drone 1, drone 2, they have different IP addresses. You have your GCS connected to both of them at the same time. So far, every approach I've heard about how to solve the system has involved some sort of trying to assign system IDs, MAVLink system IDs to the two drones, such that the ground station can differentiate them. Let's forget about that. Let's just use the IP and port where these drones are and connect to them and interact with them. So there's no need to assign MAVLink system IDs. Same for multi-GCS. So there's no need to assign different system IDs to the different GCSs. Just communicate with the drone as you would with any internet-based system, as long as you're on an IP network. Yeah, takeaway. Let's not try to assign system IDs. Let's just differentiate systems by IP port. So when you get data from an IP port, use that. And yeah, let's think about encryption, authentication. I mentioned DTLS, which I think is probably the right thing to use. More questions will arise about how do you do key management, and maybe want to standardize that. And yeah, we can see about that. So how to get started? Interestingly enough, quite a lot of companies do that already. And they may do that unknowingly that they do it that way, because they don't provide a UI for you to set up the system ID, and then they're kind of already doing that. For example, Skydio is a good example. So Skydio is MAVLink compatible, and you can't change the system ID, and actually you can just identify it with the IP address, and it actually works out right out of the box there. There's also an effort called RAS-A, which is a US government standardization effort that is based on MAVLink. And there it's also now codified in the standard like this, that system ID is pretty much ignored, and drones should be identified by where they are based on the IP addresses. Then something that we've built is a fully open source, free open source library called libmav, which most of all, it's just a much easier way for you to use MAVLink, but on the other hand also implements this pattern of just not caring that much about system IDs and using IP-based networking instead. So I'm sure you're familiar with the traditional way of having the generator to generate the C code or the Python code or whatever to get into your app right? So you have the message definition, you use the generator, you get the code, you link against that, and then you send it out the wire. And so the libmath library that we've built makes this a lot easier, so you don't have to compile or you don't have to generate anything anymore. You can just load the XML at runtime and just use it, right? So you just import the libmath library into your program, you load the message definition XML file in your program, and you can start encoding messages, sending them, decoding, encoding, sending out the network. So this makes it much easier to use. This is how it looks like. So you can really just say, message set, this is the XML I want to load. You can even add inline messages, like, oh, here I want the new message, and just add it, and that works. Then you can use this. This is C++, even though it looks like Python, but you can really just fill in the message like you naturally would, rather than like doing memcopy and C things. Yeah, that's quite nice. But most importantly is that it does implement this routing scheme. So here we do this network runtime. So this opens the ports and sets up the networking for you. And then there's this on-connection callback. So whenever somebody connects to your endpoint, your MAVLink endpoint. Now, traditionally, the on-connection would have been called whenever a new system ID has connected to your endpoint, no matter from which IP it would come from. But we changed that. So here, it's on-connection is really a new physical IP connection or a new IP port combination that has tried to reach you. So it's now based on IP networking. You can still use libmath to do the old way. You just have to do it yourself, right? Then you have to go and check for the system ID and do the whole MAVLink magic yourself. You can still do that if you want. But yeah, this makes this actually quite easy. Cool, yeah. It's free, it's open source. You can use it, you can contribute to it. And that's that. For the component ID, that we still use and recommend. We can maybe talk next year about how we can get rid of that. And for the TCP re-implementations as well. But yeah, one step at a time. Cool, thanks all. Any questions? Yes?
So I saw LibMav like 2 days before I came to this conference.
Yeah.
I thought it was really interesting. We're using Mav SDK, and I'm wondering, what would you say your biggest difference besides the Mav SDK?
Yeah, I mean, I like often to sort of split the MAVLink stack into the stuff that's really well defined and is quite nice, and you can argue about it, and the stuff that's a little bit wonky on top. And libmath implements everything that's nice and well defined. So it implements message serialization, deserialization, networking, these things it does for you, and it adds a great API, a very easy to use API to use these things in MAVLink. Mav SDK is much higher level. So Mav SDK is really more geared towards you implementing a ground station and wanting to do things like call a single function call to upload a mission to my vehicle, and then there's 1,500 messages being generated and exchanged under the hood for you. That should be transparent to you. Whereas in libmath, you're actually responsible for this, right? So if you mission upload, it's not that a complicated protocol, so you can probably fairly easily make it up with libmath. But if you would want to do Mav FTP with libmath, it's probably a bit annoying. Yeah. Then you probably want to use Mav SDK. We could add these higher level protocols to libmath as well. I mean, or add another project that implements wrappers for the higher level protocols in libmath. I mean, contributions are welcome. Yeah. Also, Mav SDK uses the standard C library. Like the Mav SDK is, whenever you build Mav SDK, it's built against the version of the XML that you built it against. And then you need to recompile the entire library if you add a message, whereas libmath is all runtime defined. So that's quite nice. So Julian that is maintaining from Mav SDK has actually asked me to make Mav SDK now based on libmath. And I think he's working on something there, but I don't know how far he went. Okay, yeah. I think that would be quite cool, yeah. That would be cool if we could do that, yeah. Yeah?
Do you think the scalability issues would show up, and what do you think that would look like?
You just get a lot of traffic on, if you have the the more nodes you put on the network, the more broadcast traffic you generate. So each node you add at least generates a heartbeat. So when you have 100 systems on the network, every component on the network receives 100 messages per second just for all the other systems to announce themselves that they exist. And as soon as you have, let's say you're a GCS and you have 5 drones connected. You probably do care about the telemetry from all the 5 drones. But let's say you're a parachute on the drone, and you receive the full telemetry stream from PX4, like battery status of PX4, and you probably don't care about that. And you still have to parse it, you still have to look at it, you still have to do that. Yeah. So actually my solutions here that I presented also don't really answer that question. And I mean, my answer to this is, if you're going to do inter-process communication on board a vehicle, just don't use MAVLink, use DDS, use ROS2, use some other protocol that's built for that, because you don't need the features of MAVLink. So MAVLink is for radio links where you have low bandwidth, you have dropouts, you have these kind of things. But I mean, if you're on board and you want to use something like ROS2 or DDS or something. Yeah.
Why did you drop the code generation step? Don't you think that would lead to some unnecessary runtime impact?
I mean, the biggest overhead of MAVLink is not the filling of, I mean, we did a lot of benchmarks there. And actually, on a Linux system, on your average Linux system, even an embedded one, libmav is not slower than the generated C code. It's just quite fun because it's completely runtime defined, and it's all using dirty dynamic allocation and all the forbidden things. But yeah, it's actually about the same speed. The biggest overhead in MAVLink is actually the UDP packets. It's that for every MAVLink message, so MAVLink messages are very small. They're like a couple of bytes, right? I mean, the maximum message size is 200 bytes, and the maximum UDP package size is actually like 16 kilobytes or something, or even more. And so for every MAVLink message, we send a UDP packet, and actually the network stack in Linux that sends the UDP packet is actually the bottleneck. So if you really want to make MAVLink faster on Linux, you should do something like coalescing of messages into UDP packets or stuff like that. I mean, that's the real bottleneck of the system. But even that, it's not like, I mean, it's such a simple protocol, it's not that big of a deal. Yeah.
Are the drones expected to have like static IPs assigned to them by like a ground station, or is there some sort of like DHCP situation with like if you have drones connected to each other, how does that work?
So that's a question I get asked a lot, and the answer to that is, do we want to put that into MAVLink, how somebody builds up their network? And maybe we want to. Maybe that should be something we put into MAVLink and said, oh, the IPs to the drones shall be assigned using DHCP and that address range or something like that. Or we don't. Or we say, this is actually out of the scope of MAVLink and this is something else. I personally believe it should probably out of scope for MAVLink. Because, I mean, at the end of the day, it's just how do you set up an IP network where everybody can reach each other? And everybody has such different requirements. I mean, people want VPNs, people want this. I don't know if MAVLink could live up to that to answer this. Cool. One more.
I have several questions.
Uh-oh.
Is IPv6 supported?
Sure. That's the nice thing about layering, right? We don't care if you use IPv6. You don't need to use IP at all, actually.
The second thing is how, if you talk about a multi-vehicle setup, how, and you are saying all the systems IDs should be one, how does the ground control deal with that, and how is it showing up at the ground control side if everything is one?
Well, because it receives it from different IPs and ports.
So we have already libmav integration with the ground control?
We do not, but we welcome PRs. Yeah, exactly. That's the part that would have to change the most, is that in Q ground control that we differentiate the multi-vehicle not by the system ID, but by where the data actually comes from. Yeah.
So is it planned to happen? So
I mean, I can't speak for Q ground control community, but it's definitely planned that we do it at Auterion in our fork of it. Yeah, I guess Q ground control maintainers have to decide. Yeah.
At what sort of level radio are you going to be able to use this system? Because obviously using IP radio, what's the cost difference? I know that a lot of people don't want to go down this path because they're still using through the ROs, radio, whatever.
I mean, honestly, you can even do IP over serial links. So that's, if you remember 65K internet over the telephone thing, that's exactly what that was. That was a IP over a serial link. So, I mean, you can do that. And a UDP overhead is not that big. So, doesn't work? All right. Well, yeah, then I don't know. Yeah. It's terribly slow. Okay.
But I ask a different question. As we scale and new aircraft come into the system and leave the system, as opposed to, here's my collection of assets that will fly together and more full. How does this story work with MAVLink and IP? Like, is there a separate IP network processing in the background of these things, granting IPs, and then MAVLink becomes the opposite of it?
Do you know, I mean, the system you're describing now is sort of the holy grail, right? So you want a decentralized, self-configuring system with auto-discovery and all of that. And honestly, also MAVLink doesn't do that. I mean, in the old MAVLink, you had to manually assign system IDs, and then on top you had to actually set up the IP network, and it didn't really solve that either. I don't think this solves this issue. I think what you're describing, you need another protocol. And yeah, I know Peter will have a talk about CNO. Maybe that will be more in line for a use case like that. But I mean, we could standardize things like that. I don't know if they should be in the scope of MAVLink. Maybe they should be. But it's not something current MAVLink has solved. And doing this actually probably brings us closer to something like that, because then we could use some existing mesh network technologies. And yeah, I mean, at the end of the day, there are really cool mesh network technologies out there that do IP meshes with dynamic rerouting and relays and discovery and everything. And maybe we could just use something like that. Yeah. Also link aggregation, also multi-link setups with deduplication. And yeah. Cool. Right, I have to go. I get the sign. Thank you, everybody.